Hello, and welcome to Physics with Mr. Elliott. Today I'm going to go over some momentum, multiple choice questions, but I'm going to show you the work for them without showing you the answers. So we're going to talk through a couple different types of questions, impulse and elastic collisions more specifically. So to start, we're going to look at the first situation is a situation where I have a tennis ball bouncing off of a racket, and we're being asked, what is the change in momentum? So the question is, a tennis ball approaches the racket with a momentum of 5 kg/meters per second and bounces back with a momentum of 6 kg/meters per second after the collision with the racket. What is the change in momentum? First, I want to point out one of the things that we're talking about here. It says change in momentum. Looking for delta P, which you may remember is also equal to the impulse given to the tennis ball. So the change in momentum is equal to the impulse. Now, one of the biggest mistakes, and I'll start off with that I see is students see two numbers, 6 and 5. I'll see them either add, I'll see them subtract them and say, well, the change in momentum must be 1. Now I'm going to show you today why that's not true. So, to start off, we need to know what momentum we started with. We need to know what momentum we finished with. And luckily enough for us, that's given to us in the problem. We don't have to do any m times v or anything like that. So, momentum we started with as the tennis ball is 5 kg/meters per second. But notice the direction, and that's where I see a lot of mistakes. It's going to the left. I'm going to make that negative 5 meters per second. And the final momentum is to the right, and it's 6 kg/meters per second. Now that one's positive because it's going to the right. So I go back, I'm looking for the change. Anytime we look for the change in anything, we always do what we finished with, or the final, minus the initial. So momentum, change in momentum, nothing different. Final momentum minus initial momentum. Final momentum, we have a 6 minus, and this is where I said before, if you just subtracted 6 minus 5, you would get it incorrect because it's minus negative 5. And that becomes 6 plus 5 because we have minus a negative, which is 11 kg/meters per second. One quick note, if we were asked anything else about this situation, we probably would want to think about the force applied on the tennis ball to give such an impulse, because change in momentum is equal to impulse. And I want to show you that impulse is also equal to force times the amount of time that force is given, or delta T. Alright, so let's move on to our next question. In our next question, we have an elastic collision shown by a bowling ball colliding with a beach ball. As we look at this bowling ball and this beach ball, we want to think about what type of collision is it, and how can we understand what equation to use, but more importantly, think about what should the answer be like. Not what should the answer be specific, but does it make sense? And the way I think about it, if I have a big bowling ball coming in and hitting the beach ball, that beach ball is going to go a lot faster than what the bowling ball started at. So we're going to look for an answer that's bigger than v. So I read the question. The bowling ball moving with a constant speed v collides elastically. Key word there, elastically, with a stationary beach ball. Another key word, stationary. We'll come back to that in a second. After the collision, the bowling ball barely slows down. What is an approximate speed of the beach ball after the collision? So, we have some velocities given. We know v1, which is the bowling ball, is v. v2, which is the beach ball, would be 0 because of what I highlighted as stationary. We have v1 prime, the velocity of the bowling ball after the collision. Well, it doesn't slow down much. So we're going to approximate that as still being v. And we're going to look at v2 prime and find that. Now, some students will think, well, that must mean that the beach ball has a velocity of 0. But again, think about that logically. It doesn't make any sense. The beach ball has to gain a velocity when the bowling ball hits it. So let's investigate with our equation. Because it's an elastic collision, that means we can use V1 minus V2 equals negative V1 prime plus V2 prime. An equation we gathered from the idea that the kinetic energy is conserved as well as the momentum. Putting them together, we get this massless equation. So, I'm solving for V2 prime. All I need to do is add V1 prime to both sides, and I will get V1 minus V2 plus V1 prime equals V2 prime. I plug in my givens here. I do V minus 0 plus V equals V2 prime. Well, V plus V, adding like terms, we get 2V equals V2 prime, and that is our answer. So it's going to be double the velocity of the bowling ball, which makes sense. A beach ball is going to be moving faster than the bowling ball after they collide elastically. Remember, elastic collision means we can use this massless equation. I would not use this for a collision that we did not know was elastic, or we didn't know the kinetic energy was conserved. Let's move on to the next question. All right, question number 3. In this one, block A with a mass M moves on a frictionless horizontal surface. So I see mass M, we do that box, at a constant velocity V, do that one too, and collides elastically, big key word, with an identical block. And I'm really going to highlight identical for us for a second. What is the velocity of block A after the collision? So right away that tells me I'm going to look for, I'm going to call this VA, and it says after the collision, VA prime is what we're looking for. And what we're given, we know that VA initially, we can look at our diagram and our question, equals V. We know that VB initially, well, we see in the picture, and we also read that it was at rest, so it's 0. And we know we're looking for VA prime. Well, we can't use our elastic equation collision, collision equation because it's not given to us. We don't have VB prime. But we highlight this term right here, identical. What that means is when I have a collision of two identical masses, that's elastic. I know it's a lot of ifs and whens, but if I have such a collision, they literally trade velocities. So that means that VA would give its velocity to block A would give its velocity to VB, and block B would give its velocity to VA after the collision. Let me show you that in terms of this diagram. Block A has a velocity of V. It collides. Block A is going to stop. It's going to take the velocity block B had first. Block B is going to continue moving on with the velocity block A had before. The collision literally is just a transfer of velocities if we have identical masses in an elastic collision. So, the VA is now 0, and VB prime is now V. So to answer our question at hand, VA prime is equal to 0. It gained the velocity that B had before. Okay, that's an elastic collision. We've seen some examples of that. I will be uploading a video of such a collision as well. Alright? Thank you for watching #Physics with Mr. Elliott, and I hope you guys have a great day.